Was it the third one that was
Oh, yeah.
Yeah, that one turned out to be smooth.
Okay, good.
Yeah, but I figured it out.
All right, so please, if you could, let's turn in the take home. Just kind of, I don't know, pass them, try and get them like this way.
When he helped me out.
Take one and then pass these back. The most fun? Is that what you said?
Most intensive.
Oh, they said most enjoyable. Did I put the wrong due date on there? No. Next Wednesday, yeah. Okay, any other take-homes? Where are they? Y'all got them over here? Okay. Thank you. Anybody else?
Oh, that's the next one.
Thank you. Okay, that's it. Okay, make sure you turn in your take-homes. And just set them right here on this corner. All right, we're gonna start a new section today, 11.5, chain rule. And there are not any notes that I usually hand out for this, just because, well, you'll see, it's a little easier to just write this by hand than it is to try and come up with a good image for it. So let's get started, all right? I will have some order to these notes, though. So first note, 11.5.1. Recall from Calculus 1, if y is some function of x, right? Then it makes perfect sense for us to talk about the derivative of y with respect to x, doesn't it? Yes? So we could ask for dy dx. By the way, did y'all have a good weekend? No? Okay, I'm sorry, Kieran. You should have had it done. You should have got it done before Friday. Then you would have had a good weekend. Oh, I handed out the new take-home. I'm hesitant to say it because I said it about the last one. Like the last one, I was, oh, it's only 4 problems. This one's 6 problems. I think this one is a little more straightforward, just computational, not as much like trying to figure out what's going on. All right. So everyone have a copy of that? Yes? All right. It's due next Wednesday. So you get a little bit of a break. Yeah. So you can start it on Tuesday night next week.
That's exactly.
You should be able to do that entire take-home exam by the end of today's class. Everything on there is through today's stuff. Okay, so remember that when we were in Cal 1, if we said y is a function of x, then you could actually talk about what dy dx meant. Now I'm going to start doing stuff. It's going to look a little weird at first, but you'll see where we're going with this, all right? So I'm going to draw a little picture of what's happening here. I have y, and I'm going to connect it with the line down here to x. And what I'm saying is that y is kind of higher up on this diagram, x is below it, which means that in order to know y, someone needs to tell me what x is. So if I have x, I will be able to produce y. So this is kind of like the root, and the tree is growing out of this, all right? So it makes sense for us to talk about dy dx, since y depends on x alone, right? Someone gives you x, y can be determined, right? All right. Baby steps. Whoa. Need some more room up here. Now, what if you have this? 11.5.2. What if you're given that y is some function of x and that x is some function of t? I'll do it this way. X equals g of t. So y is a function of x. Shut it, please, yes. That means if someone gives you x, you can determine what y is, right? But over here this says in order to know x, someone has to give you what? T, right? So if I try and draw this diagram again, what would be the letter that would be the highest point on this diagram? Y. Okay, so we have y. Y would depend on what? It's supposed to be straight down. Y would depend on x. And x would depend on t, right? So when we link these two variables together, right, it makes sense for me to talk about the derivative of y with respect to x, doesn't it? And when I link these two together, it makes sense for me to talk about the derivative of x with respect to t. Yes? This all makes sense? And so back in Cal 1, if we were looking right here, y ultimately depends on t, doesn't it? Since y depends on t, which you can see it from this diagram also, right? T, you need t for x, you need x for y. Then we can ask for dy dt. That would be the rate at which y is changing with respect to t. So you change t by a little bit, that changes x, in turn that changes y. So we can talk about the instantaneous rate and change of y if there's a little bit of a change in t. Yes? We good? So what is this by the definition of chain rule from Cal 1? If I want to know what dy dt is, it would be dy dx times dx dt. That's what chain rule from Cal 1 would have told us. Now I'm going to give you an example of this right after this so you can see how this works, all right? But it's almost like these dx's cancel, don't they? Dx, dx, and you're just left with dy dt. Now, back in our picture, do you see that to find dy dt, what you do is you take the product of these two down the tree? Do you all see that? Now, we only have one branch to this tree right now. So it's hard to talk about it as a tree because there's only one branch. But we just multiply these two, and that would define the derivative of y with respect to t, yeah? Okay, so let's look at a specific example of this. Let's see, we'll call this 11.5. Example 1. There's nothing new here, okay, yet. It's just a different sort of notation. Let's say y is equal to x squared, and let's say that x is sine of t. Find dy dt. So what it'll be is the derivative of y with respect to x times the derivative of x with respect to t, right? That's what I just said on the previous note. And what is the derivative of y with respect to x? So come over here, take derivative on both sides with respect to x, and what would you get? 2x times now derivative of x with respect to t. So take derivative with respect to t on both sides. dx dt is equal to cosine t. And then what we could do next is get everything in terms of a single variable. Like right now I have x's and t's mixed, right? So I'm going to replace x with sine t. And this would give me 2 sine t cosine t, right? Now, of course, that's an identity, isn't it? Just so happens to be. That's sine 2t. What's that? What's wrong?
There was a problem like that from the test.
Oh,
There was a trigonometric identity like that.
yes, sir. I remember.
No one believed me.
No one believed that that was true? I believe you. I believe you. Are you talking about the one with trying to find the maximum speed? No.
Yeah, it was.
Okay. Yeah, so you could use this identity or you could have not. I think you could have left it like that also and still done it. But okay, all right, so look, this all seem okay to you?
Where did the X go?
This x right here? I replaced it. And that's just because I want everything in terms of t. So I just went back up to this right here. Now let me rewrite this problem in a different way, okay? I'm gonna just change things up a little bit. What if I take this right here, okay, and I rewrite that, but let's actually just plug in x right now before we take a derivative. X is sine t, right? So this is really sine squared t. And if you were asked to take the derivative of this with respect to t, you would do chain rule, right? So the 2 would come out, be 2 sine t, then times the derivative of sine t, which would be cosine t, which is this answer right here, right? So that's this right here, what we did when we do this in Cal 1, this is chain rule, right? But now we're kind of looking at it from a different perspective. And you'll see why in just a moment. Okay, you just have to hang tight for a second. No questions? All right. So what if now 11.5.3 what if we have z is equal to some function of x and y? What do you need in order to determine the value of z? You need both x and y, don't you? So if I'm going to draw a diagram of this, I have z up top, but it depends on both x and y. So I would have to draw 2 lines coming off of this. This would be x, and then this would be y, wouldn't it? And let's think derivatives. When it came to derivatives of this from last class, we said that there were how many different derivatives we could get from this? There were 2 that we talked about. One of them was the partial with respect to x. The other one was the partial with respect to y, right? So what happens in our diagram is if we're going to try and talk about a derivative going from here to here, or a derivative going from here to here, it can't be a straight derivative like in Cal 1 because we're holding one variable constant. So we call them partials, right? And our notation would look like this. Partial of z with respect to x, right? That would be down this branch. And then down this branch, partial of z with respect to y. Does that make sense? Those are the two derivatives that are possible. Right? Those are the two derivatives that are possible. So anytime you have a diagram where a single variable needs two different variables in order to determine, right, what the value is, down those branches have to be partial derivatives. They cannot be straight derivatives like Cal 1 unless the branch goes down by itself like in the previous problem, right? Then they were straight derivatives. Got it? Okay, so let's do an example. I'll do it next to this. Example 2. Let's say z is equal to x sine xy. Oh, I've fallen behind on the homework videos. It's just been busy. I've had some things come up. So my plan is to stay after today, after class, and I think I'm going to try and do 11.4 and 11.5 homework videos. Okay, example 2. So let's find how many derivatives are possible here. 2, right? That's it. Because z depends on x and y. So there's 2 derivatives possible, partial of z with respect to x and partial of z with respect to y, right? So let's start with the partial of z with respect to x. This would be equal to, I'm going to hold which variable as a constant? Y. So that means I'm going to have to do what when I do this here? Product rule, right? So product is right here. Derivative of x is 1 times the other one, plus now derivative of this one, cosine xy. Then go inside, what's derivative of xy with respect to x? Y. And then finish off product rule, x. We did that last class, didn't we? So this is sine xy. I think I'm just going to clean it up a little bit. xy cosine xy. Okay, so there's your partial of z with respect to x. Questions? Okay, now let's do the partial of z with respect to y. So what is it? Okay, x squared cosine xy. Do y'all agree? So x is a constant now, so there's no more product rule, right? Because x is a constant. It's just covered up. It'll come for the ride. Derivative of sine of xy is cosine of xy times the derivative of what's inside. What's that derivative of this with respect to y? Just x, right? So that pops out. But I already had an x out there, so x squared. So that's correct. Good. All right, so these two partials are different, right? Okay, so nothing new on this, really, just some different notation, having you draw some trees. So what if I tell you this? This is, now we're moving into the next note. The whole idea here is to get to a chain rule. Some way of taking derivatives of really complicated functions that depend on other functions. Okay, so how about this? Suppose you have z is some function of x and y. And, so I'm going to use comma for and x is some function of t, and y is some other function of t. What do you need to know in order to know what z is? T, and that's it? You need to know x and y, right? But if I give you a value of t, can you tell me what z is? Yes? Because once I give you t, don't you know what x and y are? And if I know what x and y are, don't I know what f of x and y are? See, that's different than the last problem. The last problem looked like this. In order to know what z was, right, you had to know x and y to get z. This problem's different because x and y both depend on t, right? So let me try and draw a picture, a tree. Where did it go? There it is, right behind me. Let me try and draw a tree of what's happening here. I have z on top, right? In order to know z, I need to know x, I need to know y. What do I need in order to know x? T. What do I need in order to know y? T. You see that to get from the bottom up to the top, all you need to know is t? Yes? So let's talk about, yes, question?
Is the t going to be the same for both of them?
It'll be the same t. So you could, and I've seen some people draw it this way, is they put them like this. You could do it like that. Do y'all like that notation? I can go with that notation, yes? I think that's a little different than the book, but I think we can all agree with that. That's all right? So if I know t, I'll be able to get all the way back up to z, yes? So z depends on just t, yes? So what derivative is possible? dz dt. dz dt. So partial or straight? Let's think about this. A partial derivative is only used when we have to hold one variable constant, right? Here, I don't have to hold a variable constant because they share the same thing. They get their values from the same place, right? T goes in, x is determined, y is determined. Those come in and get you z. So z depends exactly on t instead of in the previous problem where z depended on two different things, right? You have to give them both. Okay. So this derivative is possible. The question is, what the hell is it? What is it then?
dz dy times dy times
Couldn't you just put x and y into
You can go either way.
Yes, you could go here and here, but look, it could get a lot more complicated. That's what we're trying to do is come up with a general pattern of formula that will work. Okay, so let me come back to this tree. Now you'll see kind of why I did things the way I did earlier. Do you remember I said if you're ever going to go from a variable to split across, if you're going to talk about the derivative along this branch, it'll have to be a partial, right? So you agree to go from here to here as a partial z with respect to x, yes? And do you agree over here would be partial z with respect to y, yeah? Now, what about going down the branch here that goes from x down to t? Is that going to be a partial derivative or a straight derivative? Straight, because it's going to be x depends just on t. So this is dx dt, understand? And down this way, it's what? dy dt. Okay? Any questions on that? Now, let's imagine that y wasn't here. Isn't that the problem I gave you a minute ago where z depended on x, but x depended on t? And what did I say the derivative of that was? Do you remember? Yes, and you just multiplied those two pieces together, didn't you?
Yeah.
Right? Now we have two pieces instead of just one. See, this was chain rule right here. It was down here. We do that times this. But now that we have another branch, here's what we're going to do. dz dt is going to be the partial z with respect to x times dx dt. So that's this branch, right? Plus, okay, plus the product down the next branch, which is partial z, oops, that's a partial y. What's that? I didn't hear that. Did you say that's just wrong?
No, that's just bizarre, man.
Yeah, it is kind of odd, but look, if let's just say for the sake of trying to make it make sense as to why this works and why this is not multiplication, because that might be your question, like why isn't that multiplication? Just chain them all together, right? Maybe. I don't know. Think about it this way: what if y is the zero function? Okay, so y is gone, really, right? Because the derivative of 0 is going to be 0. You should still have a derivative. You should still have something. And so if y is 0, this whole side is gone, isn't it? And all you have is this. But if x is 0, This should be gone, but this should still be there, right? This is the way you can make that happen with addition. So if the y function's gone, this part's gone, you still have derivative on the other side. Here, if that's 0, you come to the other. Does that make sense? So that's why there's addition between the two. All right, so let's do an example of one of these. And we're going to go back and we're going to look at the same one we just had. That'll make our life a little easier when it comes to these derivatives. X sine x, y. That's what we had before, right? The problem right before this. But I didn't tell you anything about x or y, right? I just said that's it. Now I'm going to tell you something a little bit about x and y. X is going to be t squared plus 1, and y is going to be natural log t. So let me act like I'm just starting this problem. All right, I'm sitting there, I open up my book and I'm doing a homework problem and I look at this and it says, the question is going to be, what derivatives are possible? Okay. I think this is, where's the take home? Can I look at that real quick? Slide over. This is very much like number 6. Determine what derivatives are possible. Draw a tree diagram and label all branches. Find a formula for each possible derivative, and then find each derivative. So that's pretty much the way you want to approach this. All right. So first of all, what derivatives are possible here? So the way you answer that question is you look at the top variable, which we said was what? Z, and you look at the bottom variable. There might be 1, there might be 2, there might be 10. What's the bottom variable here? T, right? T is the bottom. So as soon as you know that the z can be determined from t, ultimately, there's only one derivative possible. It's the straight derivative dz dt, right? So I like to draw the tree first before I determine z, x, y, t. So dz dt is only possible derivative. Do you have any questions on that? Then you come through. I know we just did this a second ago, but I'm doing it again. We say, hey, z splits apart, so I know if I'm going to go from here to here, it has to be a partial. Here, partial. X to t, there's only one line going there, so this is straight. Same thing over here. This derivative will be, what's some language I could use here? This derivative should be the sum of the product of the branches, right? The sum of the product of these branches. So dz dt should be the sum of the product. Here's the product of the first branch plus the product down the second branch. There. And let's actually compute this now. What is the partial of z with respect to x? We did that just a moment ago, didn't we? Partial of z with respect to x. It turned out to be sine xy plus xy cosine xy, right? That was just that piece, right? I'm going to put that in parentheses. Times, now what's dx dt? Come up here, dx dt, right there, 2t. Understand? What's next? Add, so plus. Now, partial z with respect to y, which was, we did that a second ago. What was it? X squared cosine xy. And then times dy dt, which is 1 over t. That's your derivative. However, z depended on t, right? which means that my answer should just have t's in it. So what I'm going to do is just go back to this, and everywhere I see an x, I'm going to replace it with t squared plus 1. Everywhere I see a y, I'm going to replace it with natural log t. I'm going to write the whole thing out. That's the derivative. I'll put it right here. So this dz dt is equal to sine of, so I'm doing this, x times y, so that's t squared plus 1 times y natural log t. That's just that, right? Plus, what's x times y? Shit, again, t squared plus 1 times natural log t. But then that's times cosine of, again, t squared plus 1 times natural log t. Close off my big parentheses. Yes or no? Yes? It's just tedious at this point, isn't it?
Yes.
Then this times 2t. Now I could distribute the 2t through these, but I'm just going to leave it for now. I'm only right here, right? That's where I am. I'm right here at this point right here. So then plus, and then this right here. So I'm going to need a new line for this because I don't want to go off the screen. So plus x squared, which is this squared, so t squared plus 1 squared. And then cosine xy, well, I have that already. Cosine of, here's x, here's y. And then finally, times 1 over t. That's it. That's how chain rule works when you have functions of more than one variable. Questions? Yes.
So, like you were saying for the other problem, if you replaced x and y with the functions to begin with, and then took the derivative,
Mhm.
you'll end up with the same thing.
Yeah, let's see what would happen. Let's just look at it. We're not going to do it, but let's just take a look at it. What you're suggesting is, let's look at z equals x, which is t squared plus 1 times sine of x, which is t squared plus 1 times y, which is natural log, sorry, yeah, I got that right, natural log t like that. There's the original function, replacing x with t squared plus 1, right, and replacing y with natural log t. If I ask you to take the derivative of this right now, you could, right? And it would be, you would have product rule here, right? So you'd start doing that, but then when you realize when you get to this part, when you go chain rule inside, you've got another product rule. And it would be a mess, but you could do it. Like that would be a good exercise for you, you know, if you were just wanting to have fun, I guess. But this is the way you can do it.